Hi, it's my great pleasure to give this keynote lecture today at VCCA 2024. My name is Deniz Başkent. I'm a professor of audiology and also a lucky engineer who works at a clinic. The theme of this year's VCCA is AI and Hearing and the Changing Landscape of Audiology. Fitting this theme, I would like to talk about some potential new directions we are investigating in our lab for audiological tools. But before that, I would like to thank my aunt for this great photo where she proudly shows her own hearing aids, representing the relatively young active users of hearing aids who have high expectations from their devices. I think now is time we deliver those high expectations. It is a very good time for hearing devices. Our medical knowledge now has advanced a lot, and also technologies on our side. As a result, the speech perception outcomes from hearing devices have improved over many years. This figure shows that for cochlear implants. On top of that, hearing devices are now also very pretty. This makes a difference for the device users. This is an example for a pediatric processor where a child can choose colors as they like, and they are also named really coolly, such as Caribbean Pirate. Even though cochlear implants provide, on average, good speech intelligibility, still there's a lot of room for improvement. The sound quality delivered with an implant is missing in many acoustic details due to the signal transmission from an electrode to the auditor nerve. We wrote a book chapter about this, explaining what the factors involved in this limitation are, and the link is the references on the slide. The figure on the left shows the spectrogram of a recorded sentence. The amount of spectral energy is shown as a function of time. What this panel shows is that there are many rich details in the recording, such as the voicing cues. You can see these in this parallel red lines, all the formant frequencies in the voice parts of the speech. When we pass this signal through an approximation of an implant processing, which is shown in the right panel, we see that many details are lost. This version of the signal may be okay to understand speech, for some users perhaps, but it is not good enough in quality for enjoying music. Here are some examples of music that I simulated with a noise band vocoder. Usually when I play these demos in a classroom, I ask my students to guess what the piece is. So please try to do the same for yourself. And I will even give a clue. The first piece is a very rich instrumental piece with a classical music with a lot of instruments and rich music. So let's try to guess what it is. I assume it was quite difficult to guess. So I'm going to play a little bit better quality, let's say with larger number of electrodes and better spectral resolution. I think the quality is a bit better, and also because I know what the piece is, I can hear the melody in it. But even if we know what the melody is, it is still difficult to listen to this quality, I think. Now I would like to play the original piece. It's one of my favorite pieces from Beethoven, and the richness is definitely not reflected in the simulated version of the song. Now I have a second demo, and this one I also ask in the classroom. And this one has lyrics and a good rhythm, Hopefully you'll see the difference in this demonstration. So my students, all of them guess it. Also, they love this band and they love this song. But the song is so different than the classical music. The rhythm, the lyrics, it gives away the entire song. So actually, this time, the essence of the song is captured even in the simulated version. And when I play the original, you see that this one is not as badly affected as the classical music piece.
First things first, I'ma say all the words inside my head. I'm fired up and tired of the way that things have been. Oh, ooh, the way that things have been. Oh,
but in general, confirming these findings with simulations, we do observe in actual implant users, they do prefer to listen to music much less after receiving an implant than before the implantation. This work I'm presenting here is from the PhD work of Christina Fuller. She had used a Dutch version of the Iowa Musical Background Questionnaire with implant users. And what the results show is that the number of hours per day reported by implant users, the red box plot shows before implantation and the blue box plot shows after implantation. And on average, after implantation, the number of hours was significantly lower than before implantation. So seeing such results, we do have a great motivation to want to make listening to music enjoyable. And on top of that, we also would like to improve overall perception with cochlear implants. A music training study with actual implant users is a big project. There are many decisions to make. For example, which test should we use for assessment? What kind of music training could be effective, but also provide enough engagement and reward so that participants would like to continue with training. One way we can partially address some of these questions is that we work with musicians. More specifically, we use musicians as a model of long-term intense music training. There are many stimuli and many tests one can use. The stimuli can be tones or speech, or the background can range from quiet to complex noises. There are more musicians than implant users, and these tests with many stimuli that we use are less tiring for them. So this approach provides a good way of determining what test could be good to use to show a music training effect. Once we see this, then we can apply the same test to implant users. The figure shows the results of a review by Coffey et al. With which kind of test a musician effect was shown. So what we are looking for here is the studies that have a mini red circle. Our studies, lined by green big circles, they fall nicely in line with other studies that also showed a positive musician effect. Especially the speech perception test with a single talker masker seems to show robust effects between musicians and non-musicians. These are the results from a study we did a few years ago. In each panel, we have a foreground talker and a background talker. And we just measure speech perception where between the two talkers there was a voice difference or no difference. But whatever we tried in each panel, what we observed is that always the average scores by musicians, they were higher than the non-musicians. So this test seems to reflect musician benefit quite well. Next is the question of what kind of training could work. For any training to work, the activities have to be right. There must be some challenge so that there's room for learning, but it cannot be too difficult, then people give up. And engagement is also important. In the beginning of our music benefit and music training research, we have used two approaches. One was a computer-based music training, and the other one was music therapy. Before this study, I knew nothing about music therapy. And we work with students from the music therapy school in Utrecht. What we learned from them is that they use music for any clinical applications, and the idea is to use music as a therapy for any health problems. These therapists, students actually, they came up with a very nice training program, and they tailored all the lectures every day to provide maximum enjoyment and benefit for our implant users. So they chose the activities to be just right. And the activities such as telling stories to each other in a singing voice, or playing music with instruments and rhythms that actually implant users can play together. These are the results from 3 groups of implant users for a music perception test. More specifically, it is the melodic contour identification. In this panel, I show you the percent correct scores for 3 groups from left to right. The cochlear implant group, who use the computer-based training. The middle group is the group that work with music therapists, and the right group is a control group. The control group participated in group activities where they had to work together with each other, and they also had to do active listening. And they did it for specific activities, for example, cooking together or woodworking together. So there was a lot of group activity, interaction, and communication. But there was no music component in this group. For each group, the red box plot, so the box plot on the left, they shows the scores before training, and the green box plot on the right, they shows the scores after training. So in each group, the left and the right boxes show the scores before and after training, so we can make a comparison per group. What the group data show is that there is an increase in performance for music perception only for the computer-trained group, because this is the group that was trained with melodic contour identification task, and they were also tested with the same task. So I try to show it with this blue oval circle. So what that means is music training works, but the effects are also within domain, so the improvement is observed for music. Anecdotally, even though computer training seems to provide some benefit in music perception, this group reported to actually not like this training. They said they had very little motivation to continue with this training. The other 2 groups, who did music therapy or who did control activities, they did report more enjoyment. This indicates that interactions with instructors and also interactions perhaps with each other, they seem to be also a key element for enjoying training. Now, our interest was more than just music training effects, on the music perception effects. We wanted to see the music training effects across domains as well. Based on previously observed musician data, for example, we also expected an improvement for perception of speech presented in babble noise. These data are shown in the right panel, and as you can see, there was actually no improvement with training within any of the groups. So we did not see here the effect that we expected to see from the musicians. However, there was a benefit for vocal emotion perception, which in some ways falls between music and speech, because emotions rely on speech prosody, such as pitch and intensity cues, and therefore also considered as a little bit like music of speech. We think this benefit came from music therapy activities where implant users were telling and perceiving stories in songs that reflected the underlying emotions. And this is a great finding, as vocal emotion perception is a challenge for both child and adult implant users. As I mentioned before, these studies are very difficult to run. There are several challenges. Often the participant groups are very small. This is because of the generally small number of implant users, but also how many of them can actually join a long training study is truly limited. Then we have the issue of heterogeneous groups. This is to the degree that the performance before training is not always the same. So we don't always end up with the same baseline data, and then evaluating the training effects becomes also quite difficult. And lastly, control groups are also difficult to define. What activity could they do that will be comparable to the music training without the music component? This takes a lot of planning and a lot of careful selection and design of activities. But on top of that, all implant users want to be in the actively trained music group. And to solve this issue, we often offer the music training also to the control group after the entire study is completed. And what we understood from all of our music training studies is that at the end of the day, what matters most is they not only gain some benefit from training, but they also have a good time doing the training. And this is really important because we observe it increases confidence, sometimes the gained musical skills that make people feel good in social settings. And also, the more they enjoy, the more they want to do the training. The motivation stays very high. With all this experience, now we are looking into other ways of music training. For example, when I was looking into it initially, I was coming across all kinds of implant users playing various instruments. These are all real users, and they continued or learned or relearned how to play music, and they also say they really enjoy it. So because of that, we focused on playing an instrument, and I will not talk about it today, but we are also thinking about looking into singing in a choir activity. So we have done a new project now based on an entirely new method. It's called Guided Audiomotor Exploration game. And this project was a true teamwork. Our colleague from the conservatorium, Robert Harris, has developed this method. And he has done so specifically for implant users. And we also work with the cochlear implant clinical team at our hospital and music neuroscientist. Additionally, we also collaborated with piano instructors who first learned the game method themselves so that they can teach it their own practices at various locations across the country. The country is Netherlands, by the way. So this method, it does not rely on reading music from scores. It is actually made to be very practical, so it can be learned successfully by implant users. Instead, there are musical games that are developed based on patterns using only the black keys of the piano. As a result, this method provides stimulation in many domains. There's motor stimulation by using the finger movements. There's visual stimulation because the keys are visible and the contrast between white and black keys are large. And there's of course also auditory stimulation. And when this is all combined with improvisation, this leads to effective and fast learning. Going back to perception of speech in a single talker massacre, we actually saw a significant improvement in performance across the training sessions. The left and middle panels show the speech perception scores for the two control groups. The first group, shown with the red lines, was only tested, so their results show the test-retest effect. As you can see in the line that's shown in the middle, the black line, this is the average scores. This effect was not significant. The middle panel shows the results from the second control group. This group learned Minecraft, but there was no music involved. Learning Minecraft has some elements similar to learning to play piano. For example, these participants, they had to listen to instructions and they also had to use their fingers and in a very coordinated way. This interaction also produced a benefit. You can also see it in this black line, but now it's tilted, implying that there was a benefit, an increase in before-after training scores with training. The music training group, there was the right panel shown with the blue lines. This showed the biggest improvement in scores with training. So the benefit here was significantly larger also compared to Minecraft group. Perhaps what is most important is, from a practical point of view, the participants reported they enjoyed learning how to play piano, and they all could play really nice melodies. From all these experiences, we conclude that there are specific areas of perception music training can help, and a positive experience seems to be very important to gain benefits. Actually, a positive experience in general is very important in seeking and using assistive technology. If you have not seen this before, I highly recommend this enthusiastic video of Adam Savage, the Mythbuster, raving about his hearing aids. It's a great video. The link is on the slide. In a number of projects now, we put special emphasis into positive experiences that can be used also in clinical settings. One of such interfaces is for vocal emotion recognition testing of children. This game-like interface was developed during the PhD work of Leanne Nachels, and this took many years to get it right. We first worked with high school students who came up with the initial game idea, and then after this we worked with a talented illustrator who turned the idea to this interface that you see here that all children really like. And this helps us to keep their attention for a few minutes extra, but also they are having a really good time being tested with this interface. What happens with this interface is that the child hears a vocal emotion. This is spoken by the parrot, and then the child indicates the clown with the same emotion in their face. If the answer is right, the parrot throws confetti and the clowns in the background step towards the pool. And the children's motivation is so high because they really want the clown, they really want to see the clown to jump into the pool, and they go at the end like, yay, they feel so successful. It's a great interface. Laura Rahman is our PI on children's and emotion perception projects, and further we had a great chance recently to collaborate with Leuve Group, Astrid van Wieringen and Tina Aras, to work on children, a new group of children with single-sided deafness and who also received a cochlear implant. And we used interfaces similar to these in those tests. Laura and Tina, they each have a presentation at VCCA, and they will tell you more details about these great studies. And I also would like to make a point here. I'm only able to show the main researchers on this area, But actually working with children with the right tests and tools, it takes really a lot of effort and very big groups of researchers. So as you can see in the publications I put here, we have quite a large number of co-authors in this kind of projects. For the same reason, we also use humanoid robots. They really help with the engagement. We have two robots, Sam and Robin, and they can do many things. For example, they can dance. But of course, they can also test participants. Maybe that's more important for our work. And our idea here is to enhance engagement using these robots in repetitive testing that is needed for clinical and psychophysical research tests. The work I present here is based on Luke Meyer's PhD thesis, and Gloria Araiza-Yan is also here. She's our in-house roboticist. They will both give more details in their presentations on these projects. I would like to show an example here where we use the robot as an interface for the digits in noise test. It gives an image of how it can be used in the clinic, for example. So we tried this robot interface both for clinical applications in the clinic with actual child patients, for example. They loved the robots, and when they came back for the next clinical visit, they were asking about the robots. So there was a lot of popularity among children. We also use the robots by combining, for example, with the vocal emotion test, because we had the results from before from the computer interface. And then we just repeated the test again with the robot. And here our purpose was to look at the quality of the sound, test duration, to see can the robot really be a feasible test interface. The panel here shows the vocal emotion D' scores, meaning that the higher the score, the better the performance. And from both computer interface, shown in the violin plot in yellow, and the robot interface shown in pink, the scores came out quite comparable to each other. And the table in the bottom, that shows the average duration, test running times, and they were also quite similar to each other. We also investigated the user experience, and we found higher scores for positive experience, such as engagement and enjoyment for the robot. Of course, this could be a novelty effect, but still, the results show promise that in some clinical testing conditions, perhaps such an engaging interface may be helpful. In another project, we also explore how we can make the clinical test, such as the DIN test, even easier to use. The DIN test was already developed as a practical hearing test that can be applied even over landline telephones. In our project, we aim to take it one more step ahead and combine the test with the pre-trained open-access CalDNL Automatic Speech Recognition Toolkit, ASR Toolkit. Because it is open access, it makes the toolkit low cost, but that it was not specifically pre-trained for the materials that we are using, it made it unclear to what degree this combination could work. That was the purpose of the project. These are the results for the ASR recognition of the digits from 30 participants. So this is only the performance of the ASR without the DIN test combination. This is shown in word error rate, meaning that the lower the score, the better the performance. So this is the opposite of speech intelligibility scores that we often use in audiology. These participants, they were on purpose selected from a general population, and we did not restrict them on their Dutch accents because we really wanted to see the range of performance of the ASR. So what we observe here is that, except for one outlier, the ASR seems to work well for almost all participants. And there were 6 participants, which we circled here, whose word error rate was circled. The 6 participants' speech was perfectly recognized by the ASR system, such that there was not a single word that was wrong. So their word error rate is 0. Using the data of the 6 participants, we have conducted bootstrapping simulations based on 10,000 test cases by introducing decoding errors into the data from the 6 participants with no decoding errors. So the 6 panels show the simulated data based on the 6 participants. What you see here, for example, in panel 1, the first participant's DIN score came out around -8 dB. And this happened when the ASR produced no error whatsoever. And in the simulation, shown in the x-axis from left to right, every time we introduce 1 or 2 or 3 or 5, all the way to 23 errors in the DIN test. So, and we look at it, how much the error makes the threshold deviate from the true threshold. So it could be, at the end, it deviates almost 20 dB, 15-20 dB from the true threshold. But what these data show is that the combined ASR and DIN test is actually quite tolerant to decoding errors. All the way to 4 or 5 decoding errors, there is not much effect on the threshold from DIN test, and this comes from the fact that it is an adaptive test. So not every decoding error makes the test deviate from the true threshold. So the test shows a lot of promise for this reason. I hope I was able to convince you with all of our studies that with good use of technology and new approaches, we can improve audiological tools to be engaging, easy to use, provide a positive experience, but also producing reliable results. We also hope that these tools will help clinicians. Now, our next question is, how can we fully integrate these new approaches into clinical procedures? Well, we will get there, but we still need to do a bit more fine-tuning. I would like to finish my talk acknowledging my great team, both our own team but also our department. We are very lucky to work with experts from the fields of audiology, otology, neuroscience, and biomedical engineering. And they're all very smart, but they're also very critical researchers. And they also all value positive experiences and also playing music together. And I would also like to acknowledge our funding sources, because without them, no research is possible. Thank you.